In this video, we're going to be talking about triangle similarity theorems. So in the last section, we talked a lot about just similarity in general. And we have to show that if two shapes are similar, that all the corresponding angles are congruent and all the corresponding sides are proportional. So we're going to look today just at triangles and learn a few shortcuts to help us determine if two triangles are similar. The first is called the angle-angle similarity postulate, and we sometimes just abbreviate it by writing AA. And it says that if two angles are congruent, and this is in triangles, the triangles are similar. So as long as we can prove that there's two angles in a triangle that are congruent, two corresponding angles, two pairs of corresponding angles, then we've got similar triangles. So let's take a look at this example. We have two triangles, KLJ and YZX. And based on the notation in the pictures, we can say that angle J is congruent to angle X, and angle K is congruent to angle Y. So because we have two angles and two different triangles that are congruent to each other, we can say, so since that's true, then triangle KLJ is congruent to triangle YZX. Okay. So let's go ahead and look at this next set of examples and determine if these two pairs of triangles are similar to each other. So I have two triangles ABC and then PRQ. And I see off the bat that they have one angle that's congruent, this 78-degree angle. So that's great. We have one pair of corresponding congruent angles. And the 63 and the 39 are the other angles, and those are not the same. But let's figure out what these third angles are. Let's figure out what the third angle here is in the triangle, angle C. So if you remember, the three angles of a triangle have to add up to 180 degrees. So what I'm going to do is I'm going to take the angles that I know. I'm going to add them up to get 141. And then I'm going to subtract 141 from 180. And that's going to give me 39 degrees. So this third angle in the triangle is 39 degrees. And that means that that angle is congruent to angle P. So I'm going to go ahead and write that out. I know that angle B is congruent to angle R. That's one that we kind of had started with already. I just learned that angle C is congruent to angle P. So that means that triangle ABC is similar to triangle QRP. And I'm going to put a reason. So I'm going to put by the AA postulate. That means that by the angle-angle postulate, those two triangles are similar to each other. All right, let's look at B. So B, we actually have two triangles. Some people have a hard time seeing the two triangles, so I'm going to go ahead and outline one of them. One is just the bigger triangle that you see, and then the second triangle is this triangle that's kind of embedded within the larger triangle. So right off the bat, you can see that these two triangles have a congruent 41-degree angle, which is super nice. Then they actually have another congruent angle up here at the top. So the top angle in this triangle, the one at the very top of these triangles, it's actually the exact same angle. It's made by the same two sides, the same two line segments, and so it's the same angle. So what we can say that we know angle H is congruent to angle J. That's the 41-degree angle. Then we also know that there's an angle G in the smaller red triangle that's congruent to angle G in the larger KJG triangle. So since I found two pairs of congruent angles, I know that angle GHL is similar to angle GJK by angle-angle, and you can just write by AA. So those two triangles are similar. All right, let's look at this next example. So we've got these triangles here on the left. We have two triangles that are kind of meeting at one point. And it's telling us one thing. It's telling us that this angle B and this angle D are congruent to each other, which is the first thing it's asking. Angle B is congruent to angle D. So if we're thinking about using the angle-angle postulate, we've already got one pair of angles that are congruent. We also have another pair of angles that are congruent. So it wants us to look at angle ACB. So if you look at angle ACB, that is going to be congruent to angle ECD. And the reason why is because they are vertical angles. So remember, vertical angles are kind of ones that are across from each other when two lines cross. And they're always congruent to each other. So that means we found another pair of congruent angles. So we can say that angle ACB, triangle ACB is congruent to triangle ECD by the angle-angle postulate. Okay. So now I want to know what the scale factor is. So remember, the scale factor is the ratio that I get between the two sets of side lengths. So I'm going to go ahead and look at just a pair of corresponding side lengths. I'm going to highlight them in green. And it is side length AC and CE. And those are corresponding side lengths, which means if I make a fraction out of them, I am going to get the scale factor. When I simplify that fraction, I get 2/3. Sorry, 3/2. So 3/2 is my scale factor here. So let's go ahead and look at the next few sets of proportionality statements. So here I'm looking at the relationship between AB and DE. Since those are proportional sides, we know that they are going to match up with each other. And then the other side lengths we're looking at are AC, which we already have highlighted in green. I want to know, what does AC correspond to? Well, AC corresponds to EC. So that would be the bottom of that fraction there. So in this next, in F, so if we go from E to F, all I'm doing is I'm plugging in things that I know. So I know that AB is equal to 6. DE, that's an unknown value that's labeled as Z. And then I know that EC is 6. And then I want to fill in on the top what AC is. AC is equal to 9. That's the length of that segment. And then if I just jump to the next problem, I'm asked to solve for Z. So I'm going to use this exact same proportion that I've already set up in example F to solve this. So I'm going to cross multiply. I'll get 36 equals 9Z. Divide both sides by 9. And Z equals 4. So Z equals 4 based on those proportions and that's those similar triangles. Okay, so all of that was based on the similarity that we proved using the fact that we had two pairs of congruent angles. So we're going to call it the AA postulate. So don't forget that one. Okay, we're going to go ahead and learn two other shortcuts. The other thing we can do is we can talk about the side-side-side similarity theorem. Now, side-side-side is often just abbreviated as SSS, so you can totally do that in your assignments. Basically what this says is if all the side lengths are proportional, then you have similar triangles. Okay, so this means that you don't have to look at the angles at all if you can prove that all three of the side lengths are proportional to each other. So let's go ahead and look at this example that we have here, triangle ABC and triangle DEF. And I've already kind of denoted the corresponding side lengths using different colors. So let's write an if-then statement for this. So if I know that AB over DE is equal to BC over EF is equal to F, wait, let me do that right, is equal to CA over FD. If I know that all those are true, I've proved that all the side lengths are proportional, then I can say that the triangle ABC is similar to the triangle DEF. It's as simple as that. Okay. So this is just one tip that I would recommend you guys use when you're testing for side-side-side similarity and you're building the fractions. Make sure that you want to make sure that you're pairing up this right side lengths together. So you want to make a fraction with the shortest sides of both triangles, the longest sides, and then the medium sides. And we're going to go ahead and take a look at these. So we have 3 triangles in this next example. I want to know which of these 2 are similar. Okay, so I'm going to start by just looking at the top 2. So I'm going to do this work in blue. And I'm just looking at these 2 triangles. And I'm going to decide if these 2 triangles are similar. Now, I don't know any of the angles, so I'm just going to look at using the side-side-side similarity theorem. So I'm going to start setting up proportions or ratios of these fractions, of these side lengths. So first I'm going to take the shortest side lengths. So the shortest side length in the left triangle is 8 over the shortest side in the right triangle, which is 10. The longest side in the left triangle is 14 over the longest side in the right triangle, which is 20. And then I want to look at the medium length. So I have 10 over 15. Okay, and I'm going to simplify all of these fractions. And my goal is to see if they're the same. If all these fractions are the same, then I have found similar triangles. However, all these fractions are different. Okay, none of them simplify to the same thing. What you could also do if you didn't want to simplify fractions is you could change these all into decimals. So this is like 0.8, this would be 0.7, and this would be 0.67. Okay. None of these decimals are the same, which means that these 2 triangles are not similar. Okay. So I proved that the top 2 triangles are not similar to each other. So let's go ahead and check another pair. I'm going to go ahead and do, let's see, I'll just do these 2 ones on the left. We'll check these 2. I'll do them in black over here on the left. So first I'm going to look at the fraction of the longest side lengths. So I'll do the triangle on top over the triangle on the bottom. Then I'm going to look at the shortest side lengths, so 8 over 6. And then the medium side length, so 10 over 9. And I'm going to go ahead and use the technique of changing these all into decimals. So 14 divided by 12 is 1.17. 8 divided by 6 is 1.3. I'll do 1.33. And then 10 divided by 9 is 1.1. So these triangles, since they all have different ratios, these are not similar. Okay. So I checked the top 2 triangles. They're not similar to each other. I've checked the 2 triangles on the left, and they're not similar to each other. So let's check our last pair of triangles. Okay. I'm going to go ahead and just draw a line right here so I know I'm starting kind of a new problem. So let's make some ratio statements out of these. So first I'm going to take the longest side length, so 20 over 12. Let's just go ahead and change that into a decimal right here, which is 1.67. Then I'm going to look at the shortest side length, so 10 over 6, which is also going to be 1.67. Then I've got to do the medium side length, so 15 over 12, which is not 1.67, but I set that one up wrong. So this one I made a mistake on. I need to do the medium side length at the top, which is 15, over the medium side length at the bottom, which is 9. 15 over 9 is 1.67. Okay, so since I got that all of these triangles have the same ratio, it means that all the side lengths are proportional to each other. So I'm going to write a proportionality statement. Triangle ABC is congruent to triangle DEF by, and I need to say what theorem I'm using. So here I used the side theorem. So I'm just going to put by SSS. Okay. So hopefully that was helpful in understanding this side similarity theorem. We've got one more. So we looked at, the first one we did was angle, where we just looked at the angles. The one we just barely did was side, so we just looked at sides. Now we're going to look at a combination of sides and angles. So this is called the side angle side similarity theorem, and you can abbreviate it as SAS. So basically what we have to check for here is that if two sides are proportional, and the angle between them is congruent, then we know that the triangles are similar. Okay. So let's look at what that would mean in this XYZ and MNP triangle right here. What that means is that if I know, we know that angle X is congruent to angle M. So if I know that those are congruent, and if I know that the two sides that are next to that angle, so XZ over MP is equal to XY over MN, if those two pairs of side lengths are congruent, then triangle XYZ is similar to triangle MNP. Okay, so you've got to prove one angle is congruent and then that two pairs of sides are proportional. Now, it's really, really important that the angle is between the two sides that you are checking. Okay, so it can't just be like a random angle and then two random side lengths. It's got to be two side lengths and the angle between them. So let's do some examples of using these theorems. So we're going to determine whether the triangles are similar. So in this triangle in example A, first I just want to look at this angle in the very top. We know that that angle is part of both the bigger triangle and the smaller triangle. So we know we have an angle that is congruent. So we know that angle V is congruent to angle V. Now what we want to prove, I'm just going to put want to show. What I want to show is that if I take the short side, VW, the shorter side of these triangles compared to the longer side, that needs to equal VZ over VY. So I need to look at the short length, like the length of the short triangle, over the length of the bigger triangle, and that needs to equal the length of the shorter triangle over the length of a longer triangle. So let's fill in what we know. So VW is 8. Vx would be 8 plus the 4, so that's 12. I hope that that's equal to Vz, which is 10, over Vy, which is 15. Okay, so what I'm going to do is I'm just going to simplify both sides of these fractions. So 8 over 12, if I divide the top and the bottom by 4, I'm going to get 2/3. And then 10 divided by 15, if I divide the top and the bottom by 5, I'm going to get 2/3. So these two are actually equal. So I showed what I wanted to show, which means that I can make a conclusion. I can say that triangle VZW is similar to triangle VYX by the side angle side theorem. Okay. Let's look at another one. So in this triangle, kind of this combination of triangles, I see a pair of congruent angles right off the bat. These two angles are vertical angles, so I know that they're congruent. So angle LKM is congruent to angle GKH. So now I just need to prove that my side lengths are congruent or proportional to each other. So let's just take a look at these. I'm going to set up some ratios of corresponding sides. So I know that the 3 and the 12 correspond to each other because they're both the smaller number, the smaller side length in their respective triangles. So one of my ratios will be 3 over 12. Let's turn this into a decimal, which is 0.25. Then I know that the 5 and the 16 are going to go together because they are the longer sides of their triangles. So 5 over 16 as a decimal is 0.3125. That means that these triangles are not similar by the side angle side theorem because the sides are not proportional to each other. Okay, so those are our 3 shortcuts to proving that triangles are similar or not similar. So sometimes what we are going to have the biggest trouble with is just figuring out which of these 3 to use. So I'm going to run through a couple of things that can help you to figure out which of these to use. So first of all, I would recommend looking at your diagram and figuring out what information you have. Do you know angles? Do you know side lengths? Do you know a combination of angles and side lengths? Then start listing out things that are congruent. Okay, so maybe you're making a list, maybe you're marking with congruency marks on your symbol, but you definitely want to make sure you know everything that's congruent. And that's what I would do here. Write down congruency statements. Then look at what you have. Okay, this is going to be an important piece right here. If you have 2 sets of congruent angles, use angle, angle. If you've got side lengths, use side, side, side. If you know side lengths and a combination of angles, try to do side, angle, side. Okay. So as you work through this, it'll help you decide which of these 3 postulates or theorems to use and then how to use them. So I'm going to go ahead and just walk through, not actually proving a complete congruence statement necessarily, but kind of a thinking process behind this. So if I look at example A, I have these triangles that are kind of embedded in each other. So I know that I have angle D that's congruent, right? Both those triangles have that angle D. So all of a sudden I know that I've got a congruent angle. I also have information about these side lengths, which makes me think that I might want to use side angle side. So I would suggest trying to do side angle side because I have a lot of information about both sides and one angle. And the important thing is that the angle is between the 2 sides that I have information about. If you slide over to B, the 2 triangles that I'm looking at only have information about their side lengths. There's no information about angles. So I'm going to try to use the side, side, side postulate to prove or disprove that these are similar. And again, you can use these to assert that the shapes are similar or to assert that they're not similar. And then in angle C, I have 2 pairs of vertical angles, which is great. So I have a pair of congruent angles. And this one's a little bit tricky. If you remember, these little red dashes mean that these 2 lines right here, I'm going to extend, are parallel. So I'm going to go ahead and highlight one of these lines for us. If I have 2 parallel lines, then I have this red line that passes through. I know something about these angles. Okay. For example, I know that angle B is congruent to angle G because they are alternate interior angles. So let me write that down. Angle B is congruent to angle G because of alternate interior angles. So I know that angle B is congruent to angle G. I know that angle F is congruent to angle F because of vertical angles. So I can use the similarity, the angle-angle similarity postulate to prove that these 2 triangles are similar.